Okay, thank you for the invitation. So, just to explain the background. So, in the talk, I start with a reductive group over Q, and I assume that the space so the symmetric space associated to the real point of G hello. So I assume that this is Hermitian symmetric space. So where maybe K infinity is a maximal compact subgroup of G of R, and ZG is the center. And I start also with a lattice. And in all my talk, it will be an arithmetic lattice. And somehow I am interested in the Shimura variety X over gamma. And so this is a description in the analytic world, but it's known that is a quasi projective variety. This is due to Bailey and Borel. And it's smooth if gamma is torsion free. And it's projective if GQ is a Q anisotropic. So somehow we have okay, on X over gamma we have a natural structure of algebraic variety, and I will use somehow some algebraic structure of the space X itself. So to simplify the exposition, I will choose one realization of X. So I will, okay, let's X inside C power n be the bounded realization of X. So there are several, in the theory of Hermitian symmetric spaces, there are several kind of realizations. The bounded one by Irish Chandra, you can embed a symmetric space in this compact dual, maybe by Borel, or you have Siegel's realizations which are more explicit. And so all what I will say in this talk would work with any realization, and it's not an issue. You have to define the things correctly. But for the talk, okay, let's say that I'm working with the bounded realization. And so I can make a definition. So in this case, yes. But we could think about realization where n is not the dimension. It's not really an issue here. And so so I should say that immediately in the definition of what is a bounded realization, we remark that X is a real semi-algebraic set, and also a complex analytic space. So you have two natural structure, and we would like to somehow give a meaning to algebraic subset of X, which are not so natural because we have just a semi-algebraic structure. But we give the following definition. Okay, a subset Y of X is called, is said to be irreducible algebraic if Y is an analytic component of an intersection of an intersection while tilde with this bounded realization for an algebraic subvariety Y tilde of C power n. So yeah, as an analytic space, we can check that Y tilde intersected with X has only finitely many components, and any of these components is a semi-algebraic set and also an analytic set. So such a Y is semi-algebraic and complex analytic. So somehow the important thing for us is that we have a map, a uniformizing map, say pi from the realization to the Shimura variety. And there is a notion of algebraicity here. This is a quasi-projective variety. And we have now a notion of algebraicity inside this world of Hermitian symmetric spaces. And somehow we will have an interest on the bi-algebraic varieties, which will be the special subvariety of the following statement. So the main theorem and So it's the Ax link, so hyperbolic maybe. Ax Lindemann conjecture. So I think it's in this form due to Klingler, myself, and Yafaev. And okay, I will give two equivalent forms. The first one is the following. Let Z inside S be an algebraic subvariety. And Z tilde be an analytic. Okay, it's not really useful. Okay. Okay, and say directly and Y inside the inverse image of Z by the uniformizing map a maximal irreducible algebraic subset of pi inverse of Z, then pi of Y is a so-called weakly special variety of S. So if I draw a picture, I have I have my Shimura variety S, and it's uniformized by some bounded symmetric domain. And I start with a subvariety Z. I take the inverse image. And inside the inverse image, I consider Y, which is maximal algebraic inside this inverse image. And I consider pi of Y here. And I'm saying that pi of Y is essentially a sub-Shimura variety. So I want to be more precise here on what means weakly special. Yeah. So maybe I give a definition. So definition. So I want to say what is a weakly special subvariety of a Shimura variety. So let V inside S be an algebraic variety. Then we say V is a weakly special so I will give three point of view. The first one is that V is a totally geodesic subvariety of S for the natural Riemannian structure on S. And so this is equivalent to some definition in terms of group and symmetric spaces. So I want to say it in this way. There exists a special subvariety S prime of S such that, okay, either V equals S prime or S prime appears to be a product. So S prime is of the form, okay, S prime 1 cross S prime 2 with, okay, is the product of special subvarieties. And V is just of the form S prime 1 cross a point for a point x2 of S prime 2. So it's almost a special subvariety associated to a subgroup of GQ and a sub-Hermitian symmetric space, except that you can have this kind of odd situation of a product. And so this is equivalent. So maybe this is due to Yafaev and myself. An analytic component of the inverse image of Z is algebraic. So I would say that V is by algebraic. So this, yeah. So V downstairs is algebraic. You take the inverse image, you find something algebraic.
Perhaps you could explain to us why. Clarify the name Ax Lindemann. Why this generalizing?
Why it's the hyperbolic Ax Lindemann conjecture? Yeah. So you can formulate the same statement if you take the uniformization of a product of GM by the exponential and C power n. And then this is an equivalent form of, so a lot of people call this Ax Lindemann. I'm not sure it's the right term. Yeah, it's Ax theorem. So, but so it's, I mean, instead of the usual uniformization by the exponential or product of exponentials, we use the uniformization by of a Shimura variety by an Hermitian symmetric space.
One thing about Ax is the function field. There must be at least one dimension. Your varieties are all not points.
So I think, so I'll give another formulation if you want, but it's, yeah, so, I mean, for me, in the definition of anything, the dimension is positive, for sure. Yeah, for sure. And I only give a definition of semi-algebraic for positive dimensional variety, because for point is not very interesting.
Just because Lindemann is probably about points.
Yeah, it's the model we should try to, yeah, but it's not for point. It's really a positive dimensional.
Another way, I mean, think of the conjecture, simple theorem. It really means that maximum or algebra subset must be some kind of a summation.
It's an Hermitian. It's a locally Hermitian symmetric space, which is a sub. So you see, it could be the situation where you have a product and this one is not special, but still this is totally geodesic. This is exactly an Hermitian symmetric space. But
maybe your third one is the answer to my question, because you're saying that you can't be bi-algebraic except for very special reasons.
yeah.
The classical case is x and e to the x.
So somehow, if you think in terms of points, a special point of a Shimura variety is a point which is in Q bar, and for which, if you go to the uniform, you pull back to the uniformization, is also in Q bar. So it's bi-algebraic in this sense, and when you think in this way, the special subvarieties of any dimensions are just the bi-algebraic subvarieties. So, and I really think it's deeply inside the question. So, and then so V is weakly special if and only if an analytic component of pi inverse of Z is algebraic. So Z is already algebraic, and if you add the fact that the inverse image or a component of the inverse image is algebraic, then this is a weakly special subvariety. Okay, and you can think of this statement as a particular case of the Ax Lindemann.
I don't understand your equivalence. What is Z? Z is here?
Okay, so Z is V. Okay, thanks. So let V an algebraic variety. The following three are equivalent. So V is totally geodesic, or V is a product or a special subvariety, or V is somehow bi-algebraic. So it's three ways of saying the same thing. And if you want this one, if you think in terms of the Ax Lindemann conjecture, you're saying that if you start with a Z which has the inverse image is algebraic, then the maximal algebraic inside the inverse image is the inverse image, and so the object is himself weakly special. So this is a particular case. It's the basic case of the main theorem, but this one is proved by the monodromy argument, and this one by other kind of stuff. I will try to explain. So several remarks. So as I said, we can use a bunch of realizations of symmetric spaces, and in any languages, if this is meaningful, and I would say the statement is independent of the realizations of X. So somehow, what I'm saying is that if you give the right definition of realization, any realization is semi-algebraic, and any isomorphism between realization is a semi-algebraic map. And it's bialomorphic and a semi-algebraic map. So, and then you can check that.
You never really define a realization. So
yeah. So I didn't give a definition. Yeah, so Yeah, absolutely. No, but okay.
So you mean that all these realizations transfer algebraically one to other vectors? Or linearly or something?
No, in fact, the right definition of a realization is that you should have an action by the group, and this action should be semi-algebraic or semi-algebraic. And then you realize it as a symmetric space via this semi-algebraic action. And then it's somehow trivial that you're semi-algebraic because you're an orbit of an algebraic space. But okay, I don't. For this talk, it's okay at the beginning if you have one realization, and it's okay. Okay, so historically, I should say that the idea of finding this that this statement is crucial is probably due to Pilat and Zanier, and then it was it was proved by myself and Yafaev if S is projective. And it was proved also by Pilat and Zimmermann. For S equals AG, the moduli space of principally.
One point about their proof, they were using these counting arguments of Pilat,
So, but it's the one which is here.
So you're all using counting?
We're all using counting. The only difference is at one point that the counting is easier here than here and easier here than here. So it's the proof of the three statements are following the same pattern.
And this method of Mark is he also proved this?
No, he's far from. He's trying to prove such statement, but I think he has only a lower dimension. Yeah, very. But the method is very interesting. But yeah, I cannot comment. So moduli space of principally polarized abelian varieties.
I guess Pilat, his very first, on this, did use his counting.
Yeah.
Even in the case of product to GM, I don't think,
Yeah.
at that point, initially he wasn't quite familiar with X, so he kind of reproved it.
Yeah, it's okay. Okay, the moduli space of principal abelian varieties of dimension G. Okay, so there will be some O minimal in a few moments, but until now there is nothing O minimal. Okay, so I should say that that Pilat and Zanier advocated the fact that this is a crucial step in strategy for the André-Oort conjecture. So I don't want to speak too much about the André-Oort conjecture. I want more to focus on this Ax Lindemann statement, but I can somehow give just the applications to the André-Oort conjecture. Okay, so I should. Okay, I should give another equivalent form before. So I like very much this one. So it's another form. Huh? But so the way of formulating, you say let y inside X be an irreducible algebraic subvariety of X, then you take the image and you take the Zariski closure, and this is weakly special. So this is an equivalent formulation, but which is more dynamical in some sense. So you see that you're controlling an algebraic flow on an Hermitian symmetric space. And so I think this statement can be generalized or studied in very different areas. And so for the André-Oort conjecture, it's really this formulation which is really helpful. But I think this one, which is equivalent, can be generalized at other situations and can be explained in terms of measures or in terms of other things. So I think it's interesting. So why they are equivalent? Okay, it's at the same level of. Yeah. So you start with a closure of you start with Y. You take the closure and you pull back, and you have to work a little bit, but it's purely formal. There is no nothing inside. There is okay. But so corollary. You get a proof of the André-Oort conjecture for A6 for n. A new proof of the implication that the generalized Riemann hypothesis implies. Okay, I stop here. A new proof. Okay, of this statement for for a G. And so I should say that somehow both of this result are also a consequence of Pilat-Zimmermann. And somehow the state of art is that I would say that good lower bounds for the size of Galois orbit of special points implies. Yeah, so the A6 is really because of Zimmermann's result, and it's exactly inside with
the only thing missing.
Yeah. So in general, it's the only thing missing, even for the. I mean, it's not completely true, but there are two young guys working in this. The small thing which is missing here, and for the general case, and I think it's not a serious. There's nothing serious. So, okay. So the main remaining issue is this kind of good lower bound, and the best result is due to Zimmermann for say for A6, and there are some cases where you can say somehow that you have this lower bound, but it's difficult to have the general statement. Okay. So, so I don't want to even explain what is the André-Oort conjecture, because if you know, you will lose your time, and if not, I will not spend some time. So I just want to give more information on what's going on this proof. So, so the first step of the proof is a statement in hominimal theory. So, so I have to explain this. So I will say that I will state the theorem, and I will try to explain what I mean. So there exists a semi-algebraic fundamental set F for the action of gamma on, say, this bounded realization such if you restrict your uniformizing map to this fundamental set, this is definable in the O minimal structure R and X. Okay, so I have a lot of things to explain. So I have to explain what is the structure R and X. What does it mean that it's O minimal? And yeah, and after, so I must say the less, but to give an idea at least. So I would say that R and X is yeah.
What do you mean by fundamental set?
So I mean that if you take gamma times F, you find you find X, and the set of gamma such that gamma F intersected with F is non-trivial is a finite set. Yeah, it's not a fundamental domain. It's a more fundamental set. I mean, it's easier to work with fundamental set, and the output is the same somehow, but yeah. It's surjective, yes, at least, yeah, and with yeah, the inverse image of every point is finite. Okay, so so R and X is say the collection of subsets of maybe yeah, well, it's okay like this. That you can oh, I'm not sure. No, not this sure. I don't know. It's you will see that you can. I mean, I don't want to say too much nonsenses, and but I want to give a sense of what is what we are doing. So that you can define by formulas using I would say the following symbols: plus, multiplication, for all there exist. So this is okay, and then exp, but the real exponential function, so it's important here, not so this explains the Rx here, and also what we call restricted analytic functions. So I would say that a restricted analytic function is a function from Rn for some n to R. Say with we can say with f of x equals 0 if x is not in the hypercube 0, 1 power n, and such that there exists an analytic function real analytic, yeah. Real analytic function G on a neighborhood of 0, 1 power n, such that the restriction to the hypercube of f and the restriction to the hypercube of G are the same. So typically a cosinus or a cos or sine on a small amount of periods or something like this. But you cannot consider a cosinus on all R. This is very bad for, yeah. Okay, so, and so you write formulas on the set of solutions, or what you call the definable set. And you say that a map is definable if a graph of this map is definable. So, say a function, a map alpha is definable if the graph of alpha is definable. So in, okay, now in this theory called R and X, and so, okay, so now the important point is to explain what it means to be O-minimal, and I would say that the fact that R and X is O-minimal is a deep theorem, okay, of, I would say, Wilkie and Van den Dries-Miller. And saying that any definable set in this theory R and X has only finitely many connected components.
The theory sort of quantify elimination for this
Yeah,
generalized quantifier.
yeah, it generalizes quantifier elimination, and it's so it really means that okay, you can do some very complicated things using combinations of the exponential functions, all these restricted analytic, equalities, whatever you want. But at the end, it's not too wild. You have some finiteness assumption. So it means it's equivalent, in fact, of to saying that the only definable subset of R are just finite union of points and intervals. And if you know this for R, it will imply this for all n. Okay. So, so why we are interested on such a statement? It's because there is this statement by Pila and Wilkie who work only for in some hominimal theory. So I think I need to give this statement. So So this is the somehow what we will use. Let Z be a definable set in some hominimal structure. So for example, this one. So we will define the algebraic part of Z, which is defined as the union for C inside Z with the dimension of C strictly positive and C semi-algebraic. Okay, so it's a very crude thing. You take all the positive dimensional semi-algebraic subset and you take the union. Okay. And then the theorem says that fix a height function on say q bar power n. So Z, if it's definable, it's in some r power n, and you have q power n inside Rn, and you define a height function, maybe h. And so the statement is that if you take the set of points which are not algebraic, say with value in Q or and with height less than C, then this set cannot be too big. So if you have many algebraic points with value in Q in Z, it cannot be explained without the presence of something algebraic. It's a way of saying it. Okay. And so this means that once... Yeah, I think that the starting point was the work of Bombieri and Pila on yeah. I don't think it was in a minimal setting, just analytic in the analytic setting. Yeah, but yeah, but okay. So for the strategy, it's important to have this flexibility of minimal structure, because and then to be able to use it, you have to know this statement. So I should say that this statement was done by so for AG was done by Peterzil and Starchenko. And somehow we use toroidal compactification, so maybe some heavy things, but it's a, I mean, when you have these heavy things, it's not a difficult application. It's okay. So maybe if I have time, I will just comment a little bit more, but I want to explain how we use this kind of idea in the proof of the theorem. Okay, so here is so I remind you what we are aiming to do. And here with y maximal and algebraic. And we want to say that the image of y is spatial or weakly spatial subvariety. So the way we think about the uniformization of a spatial subvariety is that there is an algebraic group which is rational inside the stabilizer of y. And the main thing you have to prove, so the main step, is to prove that okay, there exists an algebraic Q subgroup of okay, an algebraic Q subgroup HY of GQ with okay, at least a dimension of HY strictly positive, such that HY is contained in the stabilizer of y. So I would say that once you know this, the proof is not very difficult, still technical, and I don't want to focus too much. But yeah, so really, it's having this main step, which is the main issue. And so how we try to do this thing, we consider the following set. So sigma of y. And this is the collection of element in G of R or G of R plus if you want, such that the dimension of G times Y intersected with pi inverse of Z intersected with, say, the semi-algebraic fundamental domain I gave in theorem 2 is equal to the dimension of y. So as the restriction of pi to f is definable, this is a definable set in the minimal structure R and exp. And so moreover, so this is by theorem 2. And moreover, if you take okay, I need two things for all g in sigma of y. In fact, g times y is contained in the inverse image of pi inverse of z. So this is a kind of analytic continuation. And the other fact is that if you take the intersection of sigma of y with gamma, this is essentially the set such that the intersection of f with y is non-empty. So our main, the main argument is to say that gamma is a set of points with value even in Z, so in Q if you want. And we want to somehow say that this definable subset has a lot of points of small height, and this can be only explained by something algebraic. Okay, so we have to use somehow a refined version of Pila-Wilkie, but so what we really need to use this strategy is the following. So let h be a height function on, okay, I would like to say on G of Q, and for example, you fix an embedding in some GLN, and you take you take a height function component-wise on Q power n square, and you restrict it to G in some embedding, whatever. Okay. Then what you prove is that there exists a positive constant such that for any t big enough, the set of points which are in gamma and in sigma of y, and with height less than t. So this set is big. So say at least t power a. So this means that something should be algebraic inside the set sigma of y because you have too many even integral points with bounded height. So the way you use this. Okay. Okay. sorry. Okay. Okay. So sorry. So the way you use this is you find a set theta inside sigma of y such that the set of gamma in theta intersected with sigma of y is infinite. And theta is a one is in theta, and theta is semi-algebraic. And then you say something that y should be inside theta times y, because for any g, okay, because 1 is in theta, and this is inside P inverse of z. And this is semi-algebraic because theta is semi-algebraic. So theta y is semi-algebraic, but this one is maximal. And this implies that y equal theta y as is semi-algebraic. And y is maximal. Okay, and so this means that theta is inside the stabilizer, and as you have infinitely many integral points in it, theta, the Zariski closure.
A could be quite small, but luckily the main theorem says.
Yeah, A, we don't know anything about it, but it's bigger than any epsilon positive, so for some epsilon positive. So the Zariski closure is what we call Hy, and it is inside the stabilizer. Okay. Okay. So the main point of the proof is to prove this statement. And I would say that in the three theorem in the projective case in AG and in this case, the main difficulties is to prove that when you take a fundamental domain, so if you want to prove such a statement, you can start with a curve because you want to prove that an algebraic curve upstairs cut a lot of fundamental sets, of translate of fundamental sets. So the case of curve is the hardest in principle. So you take a curve, and you need to prove that the volume of a curve in a translate is uniformly bounded. And this is the main difficulty. And it's easier in the co-compact case, a little bit harder for AG, and even harder for the general case. And after, there is a strategy which is not so difficult, using some hyperbolic geometry and some volume estimates. But yeah. So, yeah, okay, this is the general picture. Yeah, I'm sorry. Okay, so at what time we could join?
I will finish on the side at 6 o'clock. So I bring like 6:30.
6:30 it could do, yes. Because I will be with some very, a girl from the institute which is traveling with me, so we will be two. we can go.
Okay, sure.
So you're going to Okunkov lecture?
I'm in charge.
You're in charge, okay. And so we could...
I can come back, I have a car, right?
we have a car.
You have a car too?
Yeah,
Okay.
we rented a car, so we could go to final.
Oh yeah, then we can go early because that's
Okay, it's
lecture
better.
finish at 6 o'clock.
Okay, so we will go at final at 6.
Yeah. Okay, so where do you want to eat? Or
whatever.
The
If
fast one is probably Chinese food.
Chinese food,
in
perfect.
shopping center, right?
Yeah,
That's how I
perfect.
use this one.
Yeah, perfect.
Then-
Because we have to go back to New York after,
Oh, okay.
and so early dinner is perfect.
Okay. So we're gonna go to Chinese restaurant. That'd be fast.
Yeah.
If you're- I mean, with the middle one, the French one, that takes forever. It takes like
Yeah.
2 hours.
Yeah, Chinese restaurant would be
Okay. Yeah.
perfect.
Okay. Then
And if you want, we go to final at 6.
Okay, that's
6 at final.
Good. What do? You can go to the shopping center, right? You can go there directly.
No, we'll go to final. Okay.
Okay,
Because
Okay,
I don't remember where it's the shopping center.
Oh,
I would find it.
Harrison Street. You live here, right?
Yeah, I know it.
Okay, good.
It should, and I think, it should be in the end that the only ineffective part is the Ziegel lower bound rather than anything.
So,
It's a nice picture. By the
So-
way, but the word hyperbolic in your title,
Is?
that for Mach, I mean, I think that, Mach's the only guy who's trying to use hyperbolicity. The word hyperbolic, yes,
No,
because your
no.
symmetric spaces are all
Yeah, it's
Hermitian symmetric spaces. Of
Yeah, when I make
negative
volume estimate, I've the
curvature.
kind.
Okay.
I don't know. It's really hyperbolic in nature because the volume estimates are really the volume. If you take the volume. Yeah.
So in the lobby, all right?
In the lobby,
The fire hall.
where in final?
I mean,
in
want
front of-
entrance? You want entrance?
See, I'm going to run, I have to go to New York.
Okay.
Now I go to Friday night, so I can drop you there if you want on the way.
No, we have a car. I rented the car today, so
Who's we? You here with your family?
I have with someone working in the development and whatever.
He moves in a different circle. No, it's a good point that he raised. He raised a good point about effectivity.
For the A here or for
Well, if you
for
define
this
the
one?
minimality with all analytic functions and
Yeah.
restrictions,
Yeah.
there's no way in which you can make the t to the epsilon
Sure.
to the function of t.
But I don't think we need
Question,
all the
exactly,
analytic
but
function. We need
One
No,
would
it's
like
some
to
of them.
He's saying
one
there should
would
be a
like to
refined
theorem
yeah.
in which these stupid analytic functions are not
Yeah.
part of the game.
But we have some of
And
them.
then
I mean,
replace the t to epsilon, say, by log or something, that will be quite interesting.
I'm not completely sure to be able to say which analytic function are exactly
No, then
entering
that's
in the
a
game.
question
But,
which should be attacked.
Structurally, I
People
think
should
this comes.
so
What's really interesting
What
is
is
the
the
only
notion
function
of-
you have to add is exponential at infinity. That's kind
Yeah.
of striking.
Yeah.
The
Is that kind of
restrictions
obvious
are-
before you
are
start?
Real analytic functions.
no, but when you
Is
look
that
at
obvious?
What?
That in these kind of arguments that only exponential is the
it's
only
because you
function
have
at
some kind
infinity.
of toroidal
yeah,
compactification
perhaps.
where
So it's always a
it's
torus.
always q
always a
exponential
torus.
to the
It's
IP
always a torus.
z1
Okay,
exponential
okay,
to
that's
IP
a bit-
z2
Yeah,
and the so it's a
Yeah,
it's a it's a complex exponential, but the imaginary
understand,
part
I
is
understand.
in a bounded.
double exponential, for example, is a terrible function. Does not exist in nature.
Yeah. No, but you could also have some cosinus.
Geometry in double exponential does not exist.
And I believe that they haven't got much further in this O minimal stuff and this quantified elimination. They can't throw in too many other functions.
No.
I
They struggle.
think that yeah.
Not yet. There are a lot of questions to study.
Anyway, it's an amazing progress. Lovely stuff.
You were the one who asked about the points on.
I started going.
Because you need
I was a
for
catalyst.
study,
I was doing Betty numbers.
Betty numbers.
Yeah, for betting, that's okay.
Let's get.
Yeah, this-
let's give you an honorarium. Now you don't
No,
take
no,
this.
no,
What
I
you
don't
going to
need it.
steal this to Ax?
Yeah, I need this.